In the era of ubiquitous digitization, miniaturization, and the pursuit of maximum efficiency of components used, no well-informed observer of the automotive market should be surprised by the solutions that are increasingly being introduced to revolutionize measurement systems and peripherals around modern engines. Highly precise, fast, and performed with a frequency unattainable for analog sensors, the measurements are aimed at optimizing engine operation, mainly in terms of ecology. Adaptations of modern engines are therefore based on a huge amount of very precise information, some of which, depending on the status given by the manufacturer, can independently make adjustments to injection and ignition maps, while others can even immobilize the vehicle. Despite training programs conducted by car manufacturers and importers, both authorized service personnel and aftermarket workshops become convinced of the use of digital measurement components only when they come to diagnose them with previously used traditional methods, such as multimeters or oscilloscopes. If a dedicated diagnostic device is able to verify the damage itself, such ignorance can last a really long time. The group of digital sensors used in modern engines also includes high and low fuel pressure sensors. They are found in both direct and indirect fuel injection engines. In the latter ones, digital sensors, which are feedback coupled to the control of the low pressure pump, measure not constant transport pressure as before, but variable low fuel pressure. Disruption of this information flow or an erroneous response of fuel corrections to the changed pressure causes immediate action of the system in the original settings of fuel maps. The observation and diagnosis of this phenomenon in LPG-powered cars was the first clear indication of the need to develop a device that is a converter, emulator of digital signals. So far, the occurring digital signals of the high-pressure sensor in direct injection engines have been ignored or ineptly emulated at the expense of combustion and smooth operation of the engine on gas. Moreover, in some direct injection engine controllers, the information about the required high pressure target does not appear in the EOBD data stream and must be obtained from the relevant PIDs of the controller. So the time has come to find a panacea for all these problems. We proudly present LAP1 and LAP2 emulators, the result of cooperation between Landi Renzo Poland RD and a specialized external electronics company. The LAP2 emulator has all the functionality of the LAP1 emulator, plus the ability to acquire the necessary information from the fuel controller, those not present in the EOBD data stream, and attach them, so to speak, to this stream so that they can be read in real time during auto gas operation. We call this extended PIDs. Functionalities of the emulator in the LAP1 version include full support for digital and analog pressure sensors, emulation of low gasoline pressure for digital and analog sensors, emulation of high gasoline pressure for digital and analog sensors, translation operation mode, translation of digital sensor signal into analog signal, ability to read or emulate two sensors at the same time, low pressure or high pressure as required, possibility of signal scaling for digital and analog sensors, list of preloaded pressure sensors, 3D map of PB low pressure for gasoline and auto gas, 3D map of PWM control signal for gasoline and auto gas, possibility of defining the minimum low pressure of gasoline during operation on auto gas, 3D map of high fuel pressure for gasoline and gas, 3D map of OBD corrections for gasoline and gas, fully programmable parameters of RPM signal, engine load and 3D map scale, possibility to save all parameters together with oscilloscope recording file, 2 CAN interface modes, querying and listening, automatic CAN protocol selection, OBD1 and OBD2 bus connection status indicator, reading and deleting OBD errors with the possibility of selecting errors to be deleted, counter of deleted OBD errors, Preview of current engine parameters. Possibility of uploading previously saved settings, maps, to the emulator. RS-232 communication interface. USB connection possible via RS-USB communication interface. We are going to present the use of the emulators on the example of specific vehicles and engines. Skoda Fabia 1.0 MPI DSGD. Digital Variable Low Pressure Sensor. In gas operation mode, there is an uncontrolled increase in fuel pressure. The fuel controller, using the available tools, which are fuel corrections of the injector's opening times and control of the low pressure pump, tries to keep the operating parameters within normal limits, but it is impossible in the long run. The original maps of the injector's openings and PWM controlling the pump are modified in a way that makes normal operation of the car impossible. A temporary solution used in such cases is the petrol contribution, or in other words, the addition of gasoline at a level of 25 to 30% during operation on autogas. Operating parameters remain under relative control, but gasoline combustion is unacceptable. LAP1, with the appropriate software, converts and emulates the fuel pressure sensor signal and keeps an eye on its correct interaction with the PMW control of the low pressure pump. Everything is done based on dedicated maps collected while the engine is running on gasoline in the full load range. Drivability and gasoline combustion remains at the level of standard MPI engines, powered by Landi Renzo installations. Opel Astra 1.4T, B14 XFL, and Buick Encore 1.4, B14 XFT. Digital sensor of high gasoline pressure and the need to emulate low transport pressure during autogas driving. As in most cases, you can simply not read the information about high petrol pressure, but this is at the expense of combustion and smoothness of driving, and requires permanent deletion of overwriting errors about its too high value. In the case of low-pressure emulator, its absence very quickly ends an adventure of driving on gas and awaits a visit to the service center for flashing the gasoline controller due to devastation of the injection map. Using the LAP emulator, we were able to translate the digital signals of the high-pressure sensor and perform the necessary emulations, which immediately produced results in terms of economy and improved drivability. With the help of the LAP emulator's second channel, the low-pressure map collected on the gasoline and the PWM of the pump control were sent in the form of emulation to the gasoline controller while driving on autogas, replacing the universal low-pressure emulator. Chevrolet Silverado 5.3, produced in 2017. Digital high-pressure sensor. This year was a breakthrough for the 5.3 engine, precisely because of the introduction of the digital pressure sensor. However, on gasoline, these vehicles are mildly more fuel efficient than the previous evolution of this engine's periphery. Omitting the pressure sensor information results in high combustion and rough transients, especially acceleration. Using the LAP1 emulator connected in translator mode, it was possible to read the digital signal of the high-pressure sensor and perform the required emulations. As a result, the owner declares such low autogas consumption that we will not even cite it, but it should be noted that the car is used very gently. Honda Civic VTEC Turbo, direct injection, L15BA. Analog petrol pressure sensor. Uncontrollable high-pressure gasoline overshoot at various points on the load map, but mainly after braking and sudden acceleration. There was jerking from an overly rich mixture, and overall the car burned a lot of gasoline when running on autogas. This was due to a lack of reading of the high-pressure set point pressure target, which is not available in the EOBD data stream. With the use of the LAP2 emulator, using the extended PID strategy, the value of the pressure target was included in the EOBD data stream. It was then possible, having a reference point to the actual pressure, to build an appropriate emulation preventing overpressure on the injection rail. Obviously, we are not able to present enormous, extraordinary capabilities of those devices in such a short material. These are just examples to show their potential. Moreover, those devices are constantly being developed according to the new challenges posed by vehicle constructors. Naturally, a detailed and very comprehensive manual in both Polish and English is also available. Lab 1 and Lab 2 emulators are both homologated according to the European Regulation No. 10 of the United Nations.